Hey guys, I'm gonna do a recording on my phone here really quick. So, as you can probably tell already, I'm just gonna keep this pretty short, but probably our last chapter, at least definitely our last chapter for those of you guys that are seniors. Try to keep it pretty short and sweet. But we're gonna start talking about oscillations and waves, and these notes are always available on Classroom as they always are. But waves are always important because it has a lot to do with energy. Okay, wave is a transfer of energy without transferring matter. Okay, it's a vibration that travels through something. So we're gonna hear a lot of words that sound a little bit the same: oscillation, wave, periodic motion, vibration. All don't quite mean the same things, but mean very similar things at least. Okay, so a wave. We kind of first start talking about periodic motion. To say periodic motion means it happens over and over again. It repeats. Okay, it's like repetitive motion is kind of like the same thing that I would say. So something that is repetitive, how would you describe the nature of that repetitiveness, or it's how periodic it is? And that's kind of what we're going to start covering today. So periodic motion, any motion that repeats itself over and over. Two terms, period and frequency, are some of the things that we would use to describe repetitive or periodic motion. Things like this could anything be from a pendulum, a clock, the heartbeat, sound vibrations, waves, really anything that has some type of repetitive nature to it. Now, frequency and period, these two terms are reciprocals of each other, meaning one is equal to 1 over the other one. So frequency is, I think, an easy one to deal with because it's like the word frequently, how frequently something happens. If you were to describe how frequently something happens, how would you describe that? It's like, how often do you get your hair cut? You're not just going to say five. Five what? 5 times a year? 5 times a week? 5 times a decade? You don't know. We're in quarantine now, so that number might actually be a lot longer now that all the barbershops and salons are closed. But anytime we're talking about how frequently something happens, it's going to have to be some amount of time. How frequently do you get your haircut? Once a month or whatever it may be. How frequently, do you, get to see your older brother or something. I don't know. It's about once every 2 weeks. It's always got to be something per time. Okay, so frequency basically tells you how frequently the cycle, the repetition happens. Okay, and we use the term hertz, the unit hertz, as you can see, abbreviated Hz there. And 1 hertz means 1 cycle per second. Now, cycle is a general term. Okay, cycle could be 1 repetition of anything. That could be 1 full wave passing by, 1 full there and back of a pendulum, 1 full heartbeat, okay? So 1 hertz means 1 per second. You hear sound waves, like a sound wave might be, I have some tuning forks that are here, I would say is like 440 hertz. That means that tuning fork makes 440 individual full sound waves every second. And it makes those by vibrating back and forth 440 times, back and forth every second. Now it seems like a lot, and it is, because it vibrates very fast. So frequently, his number is cycles per time, waves per time, cycles per time. Period, we've learned about period before, it means a time period. It means the amount of time to complete 1 full repetition of something. I think the first time we talked about is when we were doing that centripetal force lab, when we were swirling that helicopter thing above your head, and we said, well, what's the period? It's the amount of time it took for that rubber stopper to make 1 full lap around. But period, like time period, refers to exactly that. It is a time period. And it's the time, like it was in that lab, it was the time for 1 full cycle, 1 full circle. So whereas frequency is cycles per time, period is the time per cycle. They are reciprocals of each other. So frequency is indicated with a small letter f. Period is indicated with a capital letter T. And so that, to say that they are reciprocals of each other, that means period is equal to 1 over f. F is equal to 1 over T. Okay, they are reciprocals of each other. So period, we use the unit just seconds typically. And frequency is in hertz, which is cycles per second. One is cycles per second, one is seconds per cycle. Cycles per second for frequency, seconds per cycle for period. Okay, so some easy terms to start with. So here's some different items that are of note. Okay, so like the hour hand on a clock. It's period, meaning how long does it take to complete a full circle, a full lap around the clock. So that period would be, 43,200 seconds. Completes one cycle every 12 hours, in other words. But its frequency is a really, really low number. It's the reciprocal of that, because if you think about how frequently that happens, it is the amount of cycles per time. So that 2.3 times 10 to the negative fifth number there, that means that's how much of a cycle it completes every second. Now, if it takes 43,000 seconds to complete one, that means it's not completing very much of a cycle in 1 second. That's where those come from. Human heartbeat, that's, period is 1, frequency is 1. So that means, on average, your resting heart rate might be 60. So that means it is the amount of time for each individual heartbeat. And that would, the reciprocal of 1 is, of course, 1. So your, 1 heartbeat per second would be the frequency of your heartbeat. And you could look at some of those other ones there just as a conceptual understanding. So simple harmonic motion is a form of periodic motion. Okay, anything that repeats is periodic motion. So periodic is a more general term, but simple harmonic motion is a little bit more specific. And that is to say that for simple harmonic motion, that is motion in which the restoring force is proportional to the displacement from equilibrium. Okay, so think of a spring, that you have a spring, it's in its resting position, and then you stretch out that spring. Now, the more you stretch out that spring, the more it wants to bring itself back to its resting position. So that's what I mean when I say the restoring force is proportional to the displacement. You only displace it only a little bit from its resting position. It only wants to go back a little bit. But if you displace it a lot, it wants to go back a lot. Okay, so the more you displace it, the more it gets pulled back. So a spring, I think like a slinky type thing, or like any type of spring would follow that rule. So you have like a mass on a spring would be one example of that. The other example, of course, would be a pendulum. Where you think a pendulum, like the little dangly guy in a grandfather clock, you displace that a little bit from its bottom position. Okay, it wants to pull back to being at the bottom. And it keeps going tick-tock, back and forth. But the more you displace it from that, the more it's getting pulled back to its resting position. So SHM for short, that means simple harmonic motion. And we talk about this now because simple harmonic motion is very similar and is really the same thing in many ways as waves are. They behave in the same way, have many of the same properties. So the first example of simple harmonic motion is a mass on a spring. And if you can follow this picture here, again, the middle line, the blue line, I don't have a pointer when I'm doing this on my phone, but the blue line here where it's at 0, you see that right there in the center, that's equilibrium line. And position at the top row here where it says A, it is displaced and then it pulls itself back toward the center. But then it's going so fast, it goes back towards its center and then through it. So now we're all the way back to C. And at C, we are compressing the spring, and that spring wants to push it back towards the middle. And then row D here, it pushes it back towards the middle. And now it's going so fast, it goes past the middle again, and the whole process repeats. So, if you can relate the speed of the block here when its speed will be at a maximum at the equilibrium position. Speed will be at minimum at the two extremes when the spring is fully compressed, as well as when the spring is fully stretched, because it's changing direction, so it obviously stops for a moment. Okay, but, if there's no friction, this process will go on, indefinitely until, the energy lost in the compression of the spring eventually slows it down. So it keeps going and going and going, because the more it compresses or the more it stretches, the more it wants to get pulled back towards the center, and that action causes it to do the opposite on the other end of things. But when we talk about amplitude here, for a mass in a spring, that means how far it's moved away from its equilibrium position. You can move it just a little bit away or a little bit further away. If we relate that to, say, a sound wave, amplitude is like the energy of the wave, how much power is behind it in one way. But a larger amplitude means it's got a bigger swing back and forth from its equilibrium position. And again, here's a little bit of a start of a connection to when we start talking about wave motion, is that simple harmonic motion describes a sine wave. Now, going back to this slide, if we plotted a position versus time graph for this block, it would form a perfect sine wave, like you see down here on the bottom right. Amplitude versus time. Amplitude goes up, goes down, goes back through zero. It's accelerating all the time, so the line is always curvy, and how it's curvy dictates what its acceleration is going to be. So the position time graph of an object that is in simple harmonic motion creates a perfect sine wave, much like an actual wave does, whether that be in water or a pulse on a slinky, that type of thing. So that's an important connection to make here, is that how the rate that block, that mass on a spring is changing position, it perfectly describes that up and down sinusoidal type wave that you see there. And of course, we've talked about position time graphs already this year. We've talked about, we haven't talked about waves at all, but position time graphs was, of course, a really important thing. So take a moment to look at that slide if you kind of need further clarification on that. So if we're talking about a mass on a spring, what type of quantities are going to affect the period? Okay, the period refers to how long it takes to complete a full cycle. And you see on this slide an equation for that. Period is equal to 2 pi times the square root of the mass divided by k. K is the spring constant. That is a constant that is a telltale constant for a spring. A really rigid, stiff spring is going to have a high K value in newtons per meter. That means for every meter of stretch that it has, that's how many newtons of force is going to be pulling on it. So K is like a constant for the spring. Mass is the mass that is connected to the spring. 2 pi is obviously a constant. So obviously the nature of the spring, as is indicated by K, as well as the mass that's swinging back and forth, dictate the period, and in turn the frequency. But what's surprisingly not on there is amplitude. Why does amplitude, how far that mass is displaced from its equilibrium position, how come that doesn't affect the period? That doesn't make it oscillate back and forth more rapidly or more slowly? It actually doesn't. I think it would. But with amplitude, because restoring force is proportional to amplitude, the more you displace it, it's going to have to go a greater distance to get back to equilibrium and all the way to the other side, but it's also going to be going way faster when it passes through equilibrium. So the increased speed is kind of proportional to the increased distance, and it all winds up being a wash. So if you only displace it a little bit or a lot, the period of that oscillation is going to be unaffected entirely by that. The period of oscillation in these mass on a spring situations, and we're only talking about a horizontal mass on a spring, by the way, at this point, is only affected by the nature of the spring, that's the K value, as well as the mass. And if you look at this relationship, if we have a higher mass, the period will go up, meaning it will take a slower amount of time to complete a full cycle. And the K value, if we increase the K value, what's going to happen to the period of oscillation then? Think about it for a second. Okay, an increased K value means a stiffer, more rigid, more hard spring. That's going to draw the thing back way quicker. It's going to be back and forth instead of Okay, so an increased K value is on the bottom of that ratio there underneath that square root. So that means a bigger number there is going to make T, the period, smaller, which in turn does the opposite to frequency since they're reciprocals of each other. A higher K value is going to make frequency higher. It's going to be, it's going to complete cycles more frequently. And a increased mass, again, is going to do the opposite to frequency as it does to period. An increased mass is going to very much reduce the frequency. So here we see some relationships. Here's the first graph to the left. It says how we change the spring constant, and we see how the oscillation changes. If we go from the right picture to the one on the left, if we increase the spring constant by a factor of 4, the frequency would double and the period would halve. If you look at the picture on the left here, there are twice as many waves on there. Okay, meaning it is twice as frequently completing cycles. And the amount of time it takes for every one full wave is cut in half. Okay, if you see how on the bottom right how stretched out that wave is, and make sure we identify where exact full wave is here. The picture on the bottom right, just so we are aware, has 2.5 full waves on it. The picture on the right has 5 full waves on it, just so you know how to count full waves, or full cycles rather. Okay, think about a cycle. It has to complete itself. If we're talking about a mass on a spring, it goes from one extreme through equilibrium to the other side extreme, back through equilibrium, and back to where it started. Okay, it has to get back to where it started in order to complete a full cycle. So sometimes people think like half of a cycle or whatever is a full cycle, but it's not. The one on the bottom right here is 2.5 full waves. The one on the left is 5 full waves, or 5 full cycles would be the way to do that. And the change that we made when we went from the picture on the right to the picture on the left is that we increased the spring constant by a factor of 4, and you see the resulting changes. You see other similar relationships here, starting at the graph in the middle, then going to the graph at the top right, we increased mass by a factor of 4. To the graph at the bottom right, we increased amplitude by a factor of 2, which notice that the frequency of the period, just the height of the wave, the height of the sine wave changed, but we did not change the total number of waves. So when you look at the slideshow, just take a look at that and just understand those relationships. But this is all as a direct result of that equation that was on 2 slides ago. Pendulums work in a similar fashion. They are also simple harmonic motion. The more you displace them, the more the restoring force is going to be. Now, that's only true for only small displacements. If you make the angle of a pendulum way too high, those rules would wind up not applying. But when we have a low angle away from equilibrium, pendulums can be modeled as being simple harmonic motion. So gravity always draws the pendulum bob. That's what we call the mass at the bottom of the pendulum. That's what always draws it back to equilibrium. There's some fun videos here that you can look at if you look through the slideshow. But motion of a pendulum, very similar to mass on a spring. Its position time graph also makes a sine wave, but it yields the equation that you see on this slide here. The period of a pendulum is only dependent on length and the acceleration of gravity. Since, while we're on the Earth at least, the acceleration of gravity is always a constant 9.8, the only thing that we can physically change that affects the period of a pendulum is the length of a pendulum. Okay? Meaning that the mass at the bottom doesn't matter. The amplitude does not matter. As well as anything else other than length. So again, we have mass, we have amplitude, length is the only thing that matters, is the only thing where you can vary the period of a pendulum. If we go backwards one, see if this little video will play in the inset here. If this ever comes up, I'm not going to make it full screen because it's probably going to show up weird as is. But here, somebody made a cool little device like this where they put a bunch of pendulums on one thing. They all made one slightly longer than the other. And then as they did that, they displaced them all at the same time. And you can see them do that with a block of wood here. And they displace that. And we can see the patterns that arise. And it makes these fun little sine waves. And it keeps alternating too. You think it keeps changing. We're getting a totally different pattern here. Then it seems a little chaotic, and then it gets weirdly organized again, and then a little bit more chaotic, then a little bit more organized, and then they kind of gather back together and do that, and then they slowly slip away from it. But because each of those pendulums have slightly different periods, they keep working themselves in and out of this. And so you have another cool pattern like this, and you're like, oh, wow, it's almost going to stop now. But these are just getting driven by gravity. There's no motor that's driving this, and these patterns and these cool things that arise keep happening here, and it keeps going in and out of that. And you could create this at home if you want to. That actually would be a pretty cool little quarantine project. You do a cool one, I'll throw you some good amount of bonus points for you. There's a snake, but this is just a really cool thing, and it's a great demonstration in simple harmonic motion and how pendulums are only dictated by the length of the pendulum. You could do the same thing if all of those balls at the bottom weren't the same mass, still would work just as well. And this thing is still going. It's still making these cool little patterns, okay? So again, here's our equation for a pendulum. The period of a pendulum is equal to 2 pi square root of L over G. Okay, square root of the length of a pendulum over the acceleration of gravity. Yeah, so mass, amplitude don't matter. Hold on, let me click a little bit, maybe shake it. I'll stop there for now, actually. But we talked about simple harmonic motion. We'll talk about resonance. This video is kind of a cool example of that. And eventually get to waves. I'm going to keep this real quick. Okay, but if you want to work ahead at all, the notes are always on there. But a lot of what applies for simple harmonic motion also applies for wave motion, okay? So I will finish the video there and leave you guys to that. I'll put a concept builder or two up that kind of goes along with that. I'll probably make another one of these that include those items that I just kind of clicked through: resonance, the beginning of properties of waves, and so on.